Thank you, Peter. Today I'll be presenting some of the results from my colleagues from subtask 1.1. This is the culmination of 3 years of work in kind of putting together all the field experience and knowledge around the world on degradation modes, especially on new PV cells, PV materials, and module technologies. The presentation is based on a report that was published at the beginning of the year. So the credit goes to my colleagues on this. I'll be covering most of it and basically going to the most, let's say, important and new failure modes for those of you who are into PV modules and PV failures and performance. This might be interesting. So one is, which is very relevant to these new modules with half-cut cells, third-cut cells. One thing that you might have seen whenever you receive new modules from the manufacturers, from maybe some manufacturers, some of the cells might have small cell cracks at the edge of the cell. These are caused by if the cutting process is through a laser ablation process, this can cause small micro cracks. These are not a problem in itself, do not cause power loss. However, if it's combined with, let's say, improper transport and a glass backsheet type of module, this can add additional strain. And in some cases, it's an example of a new module where you have initially that was at the factory gate, and then at the installation site, after some stress during transportation, this has translated into more severe cracks that, depending on how many they are, can cause power loss of a few percent at the beginning of the PV plant. Now, this is an issue primarily for cells with ribbons. It's less prevalent for multi-wire solar cells, and it's less prevalent for glass modules. So nowadays, the majority of utility scale is glass, but you can still have backsheet glass for residential applications or lightweight applications or for older systems. Another one you might be familiar has been in the news, so to say, for the last decade, LID and LETID, so degradation caused by light and elevated temperature. This is a defect mode that has affected these P-type PERC cells, so the kind of the previous generation, especially at the beginning, was quite mysterious, and it's linked to hydrogen defects that are activated by the high temperature and the light, and they can have a quite fast time period in the first years of operation, and can lead from anywhere a few percent to up to 10% in degradation. Now, the good news is technology has improved a lot. Modern solar cells have moved on from the way they dope their silicon from boron to gallium, and this has mostly fixed the problem in P-type PERC cells, so changing this doping. And also for the newer cells that are on the market today, the TOPCons and the N-type cells, this is not a current problem anymore. So this has been fixed for current technologies and also for the latest type of P-type PERC modules. Now, another one that is quite an old type of degradation mode, but with each new generation, it's kind of resurfaces potential-induced degradation. So degradation caused by high voltage between the cells and the frame of the modules. One that has affected P-type cells, like the first generation of bifacials that we had since 2018. Especially the first generation of some module types has seen a lot of degradation on the backside due to polarization. So this is kind of a new type of degradation mode caused by carrier charge concentration on the backside and increased recombination losses. Now, this has been fixed. Also, we have kind of transitioned from these types of solar cells to TOPCons and others. But it can still be present in some of them. For PERT and TOPCon cells, this doesn't affect the backside anymore, but it can affect the front side using kind of a similar charge accumulation principle, which over time can cause increased surface recombination. And this translates in a reduced current and a reduced voltage of the cell. Now, what is also quite peculiar when we look at PID, we are usually quite easy to identify from chessboard patterns, but this one doesn't have that kind of particular degradation mode and pattern that you see in electroluminescence. So it's also a bit more difficult to know what it is at the beginning. So what can you do? In principle, mitigation solutions include kind of changing the bill of materials with more resistive or materials that increase the resistivity and the impedance of the module, be it anti-reflective coating or encapsulant. Now, one thing which is quite strange, this one is very, let's say, unstable. So the module can, in principle, recover if it's exposed to UV light. So it's very weather dependent. It also makes it quite difficult to measure in the lab because it can recover quite fast. So currently there's a new standard procedure for, or a new standards update for PID that's developed this year, which also includes adding a UV stressor during PID testing. Another one that might seem familiar, you know about hotspots. These are hot cells, which is, hotspots was more for multicrystalline where you have localized shunts because these are higher quality, they have more uniform properties. Usually the whole cell hots up when it's reverse biased. What's peculiar about these newer solar cells have a higher reverse voltage characteristic. So whereas, let's say aluminum back surface was minus 10 volts, when you reverse one of these newer cells, so PERC, TOPCon, heterojunction, they have minus 20, minus 30 volts. So when it's shaded or it's cracked, the other cells try to push current through it and then reverse bias it. The increased voltage makes it that voltage times currents, you also have increased power being dissipated in the cells, and this can cause it to reach quite high temperatures in extreme cases. So 150 degrees, which is close to the lamination temperature of the module, and you can realize what happens then. First, discoloration, delamination, the solder, depending if it gets even higher than that, the solder can start to melt. You can have insulation loss and quite severe damage. So what can you do here? In principle, trying to sort out the cells which have very low shunt resistance, which cause this high reverse voltage. There's also research in trying to optimize the number of bypass diodes. There's also modules which they try to put bypass diodes per cell by optimizing the cell kind of structure. And there's here one example of a module which has kind of a built-in bypass or Zener diode inside it. And this limits, for this IBC cells, limits the temperature in reverse to quite low, which is quite impressive. So there's some technologies trying to fix this. Now, kind of related to this hot cells is the bypass diodes. And the bypass diodes are put inside the junction, which are in principle there to protect the cells. Now, because they have become smaller, and the ribbons are smaller and everything is becoming smaller, if the manufacturing process is not very precise, the soldering of the bypass diodes can not be so precise and lead to cold soldering. So it can rebound during the potting process, or maybe they are cut too short during manufacturing, and then when you try to solder it, the contact is not that good. Or there's some reflow from the EVA, so it will act as a basically insulator for the ribbons that are soldered on the bypass diodes, or maybe there's some movement of the module layout during manufacturing, and then basically you'll have bypass diodes that are not very well soldered, and then this can fail in a few months or years after operation. Now, this combined with the high temperature of these new types of solar cells can lead to, in rare cases, to quite catastrophic result. And to make things complicated, detection is not easy in all the cases. So there are some combinations of where the bypass diode fails, where it cannot be detected with thermal imaging or normal methods that we have unless the module is shaded. And then you need to do nighttime bypass diodes testing. Other methods to prevent it would be to improve quality check during the production. Another one that is related to the module composite is backsheet degradation. And since 2016, we've had some new types of material that entered the market. And the testing that we had for these wasn't optimized or wasn't designed for them. So there's kind of three types of degradation modes that have been observed. One is micro cracking and chalking, which is not a problem in itself, but it might be a precursor to the other two. One is backsheet cracking due to hot cells. When you see one of these, you should replace the module, but it doesn't mean that your entire park has an issue. It's just a specific module because you had a reverse bias diode there, or a reverse cell. Then you can have type 3, which is caused by thermomechanical stress, either gases or, let's say, chemical degradation inside the laminate, causing gases and kind of severe cracking. If you see this, then you would need to replace quite a lot of modules. Or if you have longitudinal cracks, this is usually because you have incompatible expansion temperature expansion coefficients. And these ones can be repaired, these ones you cannot repair. Newer modules have glass now. So for these also have a problem because glass becomes thinner. But our current tests are not necessarily designed to deal with thinner glass. It doesn't include the mounting type and the clamping and all these things. So in the last years for these kinds of modules, there was quite a lot of glass breakage, especially on the rear side. So there's a lot of research now trying to develop new tests for this. The last one I want to talk about is UV-induced degradation. This is quite a new one because we haven't seen it for aluminum back surface, and it's quite specific to these newer ones. This can cause quite a high degradation rate in some of the newer solar cells in the first years of operation. What you can do here, there's still a lot of research trying to understand it. You need to add materials basically either in the encapsulant or in the anti-receptive coating or glass to block UV. And there's also new screening tests being developed. I'll skip this part. And just to give you an outlook, so as Jan said, the task is finishing soon. But there's a new one starting where we'll be participating or we'll be focusing on failure localization and trying to find methods that are both efficient in detecting failures and cost effective. And we'll also want to try to find how can we put the outputs of these methods in new contracts for PV plants. So here we're also looking for contributions from the industry. Thank you. And you can find the report. There's also very specific to failures, very to the point failure fact sheets you can also find there. Thank you.